Close. Let's get a quote. So let's see if we can make some things happy today. Happiness is sometimes what Lewis structures are referred to. And for most AP chemistry students, there's lots of happiness with Lewis structures, although sometimes things don't work out the way you want them to. So we're going to work on looking at chemical bonding. Chemical bonding, we've learned all about electrons. We've learned all about how electrons are located in specific locations around the nucleus. Chemical bonding involves the electrons and their arrangement around the atoms and how they either cause attractions or repulsions between different atoms. The first type of bonding, general bonding, is called ionic bonding. That's where you have a full positive charge and a negative charge. Table saw was an example of this. You'll see the size. Which anions are bigger? The Na in purple or the Cl in green? Okay, the Cl in green. So the size of it again changes as we know due to the periodic properties. Here, covalent bonding, this happens in water, ice is an example, and metallic bonding happens when you have pure metals or alloys of metals. Here, sodium metal has sodium ions, and the electrons flow throughout the sodium. This is why metals are such good conductors of electricity, because the electrons are free to flow around. They are not confined to specific locations. In covalent bonds, they're confined to specific locations between the molecules. And there's one other type of bond that's not up here, which is a very common bond, but it's a little harder to look at, and that's a specialized covalent bond called a network covalent or extended covalent. This occurs in diamond or in wood, where they connect together and they usually are a solid. Covalent bonding at room temperature, usually ice is not a solid, it's a what? It's usually a liquid. It usually flows better. Now, atoms gain, lose, or share electrons in order to achieve a full outer shell electron configuration. So they want to fill up that electron configuration to be like a noble gas, isoelectronic with a noble gas. Ionic bonds are composed of ions that have gained or lost electrons to achieve a full outer shell. And covalent bonds are composed of atoms that are sharing electrons to achieve a full outer shell. The reason ionic bonds stay together is because of the electrostatic attractive forces. So one is positive, one is negative, and that causes an attraction, the full transfer of electrons. The reason covalent bonds attract one another is because there's a shared electrons in between, which are negatively charged. And on the sides are the two positive nuclei that attract those two electrons at the same time that cause an attraction between the two. Ionic bonds tend to be crystalline solids, no discrete molecules or formula units. So when you say NaCl, you're actually talking about millions and millions of NAs and millions of Cls at the 1-to-1 ratio combining together to make a crystalline solid. You never ever find NaCl by itself, just one Na and Cl hanging out. You will not find them by themselves. Over here, covalent bonds usually have discrete molecules, gases, liquids, and solids. You could have glucose, for example, C6H12O6, or water, H2O. Those are both covalently bonded molecules, and they have specific units. Ionic bonds are always written as their empirical formula. And covalent bonds are identified by their molecular formulas. The really cool thing about ionic bonds is the metals are on the left side of the periodic table, left of the stair step. The stair step here goes between boron and aluminum down like this. And anything to the left of that line tends to be metal or metallic properties. And on the right side of the line tend to be the non-metals properties. If you have an ionic bond, you tend to have a metal and a non-metal. Okay? If you have a covalent bond, it tends to be non-metals with non-metals. It could be more than one, multiple non-metals together. Yes? Uh-huh. Uh-huh. I agree with you. Yep. Definitely true. Because atoms will gain or lose electrons to become ions, and then these ions form these bonds. So if you just have atoms of sodium, you don't have an ion of sodium, for example. Thank you. That is definitely right. Let's change that right now because perfect. Whoa, that didn't work out. Oh, that worked. Okay. Better. That working better? All right. So, the cool thing is about covalent bonds. We can quickly see hydrogen and chlorine. This is a simulation of what happens when they bond. Hydrogen, we notice, has one valence electron. Chlorine has how many valence electrons? 7 on the outside. And then it's got some in the middle, of course. So if we bond these two atoms together, and this here, all right, there you go. Pretty exciting. Pretty easy model to see.
So before, was it missing an electron?
Before, the beginning, hydrogen had only one electron. Helium has 2 electrons, so hydrogen wants to gain one more to be like helium. Chlorine has 7. If it gains one more electron, it'll be like argon. Okay, they'll have the same number of electrons. So they share this one and this one. They share those 2 in order for them to both be like a noble gas, isoelectronic with a noble gas. Yes.
How come hydrogen usually loses its atom and doesn't gain one? Because it could be no, it could like be fine either way. Like hydrogen could gain an electron and be like helium, or like whereas hydrogen not gain an electron.
The thing that's unique about hydrogen is because it's in that first column with the alkali metals, you would think it would lose an electron like all the other alkali metals. And oftentimes it's written that way, H+, as if it lost an electron. The reality is H+, when it's found in a solution, it's actually attached to water. So it attaches to an H2O, make it an H3O+. So if you've had biology before and they always refer to H losing that electron, the reality is it's not quite that easy. Because it doesn't just lose that electron. If it loses an electron, it's positively charged. And water is negatively charged on one end, and so it attracts, it sticks to water to make what's called a hydronium ion. We'll look at that in detail. Okay? So, hydrogen, you would normally think it could lose or gain, and yeah, it seems like it could do either, but if it loses one electron, it's not like gaining noble gas on the periodic table. If it gains an electron, it's like helium. So that's why it often shares. Like in water's case, it tries to share electrons to become like helium. Okay, so it's a small detail, but it makes actually a big difference in terms of what you would actually see. You wouldn't see H's floating around without something else attached to it. So it's a stability issue, and we'll look at that in detail. So we've seen our simulation. There we go. And then we've got multiple molecules. Would look something like this. And then what would they look like in reality? This would be HCl gas. Okay, this is like concentrated hydrochloric acid. And when you pour it, you actually see this vapor coming off. This vapor that's coming off, and it's usually found in gases or liquid, covalent. Millions of small molecules are in a covalent bond. The lengths of covalent bonds, here you can see this one is 74 picometers. HI is 161. Here are the other bond lengths for different ones. Which one has the smallest bond length of all of those? O and H, just the O and the H connecting together. Smallest bond length of all of them. Okay? And the length of bond is determined by many different things, but it involves how the electrons are being shared and the atom size. Which one has the largest? Okay, CN. 143. CO 143. This one happens to be 154 though. A little bit longer. A CC single bond is slightly larger, and there might be a reason why that is. We'll look at that in more detail. Now, bond length in general, the one pattern you could see from this data is triple bonds have a smaller bond length than single bonds. So here's our C triple N, CN, and C single N. Single, double, triple, 43, 40, 38, and 16. So that's how they go down based on that pattern. So that's one pattern you can definitely see. The other patterns about which one's the greatest and the least, there might be other reasons why that is the way it is. Now, the localized electron model is a simple model and is very easily applied. A molecule is composed of atoms that are bound together by sharing pairs of electrons using atomic orbitals of the bound atoms. There are three parts to this. One is valence electrons using Lewis structures. Two is prediction of geometry using what we're going to call VSEPR theory. And three is description of the types of orbitals. So today we're going to focus on number one, and then we'll move on to those after we get number one down. So the first part is the Lewis structure. This shows how the valence electrons are arranged. It uses dots to represent valence electrons. It was invented by G.N. Lewis, a professor at Berkeley, and it has a very, very simple model. It's the simplest model I know of to explain chemistry, period. And it's really cool because it often works perfectly. So, for oxygen, this would be the Lewis structure or a Lewis symbol of O. To do this, O is located on the periodic table. It is in the sixth column, so it's got how many valence electrons? 6. So, the electron configuration of O is 1s2, 2s2, 2p4. It has 6 valence electrons. We could get that from this too. Here, 2, 2, 4 plus 2 is 6. To draw this, you would draw 6 dots around it representing the valence electrons. 1, 2, 3, 4, 5, and then 6. The general pattern, although it does not matter where you start, is to put the electrons in individually and then pair them up. This is similar to the rule that electrons do not want to pair up unless they absolutely have to. So don't pair them up unless they have to. That's the same general idea that we saw in orbitals. Now, Lewis dot symbols for the representative elements in noble gases. You'll see here it's got 1 dot. Here they've got how many? 2. Here how many? 3. Then what? Then what? All of them have 8 except the one on the top. HE only has 2 dots on there, which may not be able to see clearly. So these are the general patterns here for drawing Lewis dot symbols. Now, if you take these symbols and put them together, you can make what is called a Lewis dot structure. Structure is usually of a molecule, symbol is of an atom. So the first rule is H and HE follow the duet rule. Okay? You could call it the duet rule if you want. You can call it the octet rule. You could call it wants to be like helium. Wants to be like a noble gas. But duet means it's got 2 valence electrons to be stable. The rest follow the octet rule. The octet rule states that it needs 8 valence electrons or none to be stable. Now, technically, none is not really true. If it loses electrons, okay, so it loses all of its valence electrons, it now has a new outer shell, a new valence shell that has 8. But if you like none, you can try to use it all you want. I don't like it. The charge species must be written in brackets with the charge number up above it. So if you're doing a Lewis dot structure for an ion, you must use a bracket with the charge number up above it. So if you were dealing with chloride ion, it would look like that with brackets with a negative 1 minus charge on it. Yeah.
So for regular atoms that are not ions, you don't have to have the bracket?
No. No, you do not want brackets unless it's an ion. This here was not developed originally by G.N. Lewis. He used his only for covalent molecules. He did not do this model for ionic compounds, but since he created the model, people have applied it. It works okay for ionic compounds, but it's just not it works okay. It's just not something that is the most helpful. It's usually used to show covalent bonding. So if we've got H here, if H loses an electron, it becomes a H plus ion like that. So that would be a way of showing the H plus ion or the hydrogen ion. Or if it gains an electron, it could now be H minus, or the hydride ion. So hydrogen ion or hydride ion. So hydrogen is one of those unique ones that could gain one or lose one to become a stable ion. Most people think of it doing this, but it can lose an electron and then attach to something else once it becomes positive. Fluorine. How many dots should fluorine have? 7 dots. It's got 7 valence electrons. Okay? How do we know? Well, it's in group 7. It's also 1s2, 2s2, 2p5. So 2 plus 5 is 7. So fluorine, 1, 2, 3, 4, 5, 6, 7. That's the Lewis structure for fluorine. Again, does it matter if you have the single dot on another side? No, as long as you have 3 that are paired up and 1 unpaired electron. It is unstable because it does not fulfill the octet rule. So it wants to gain how many more electrons? 1 more electron. It gains 1 electron. Now it becomes fluoride and it is stable. Now those are Lewis dot structures for ions. Now for compounds. A stable compound has all its atoms in a noble gas electron configuration. Atoms share bonding pairs of electrons to do so. So they share electrons, pairs of electrons, in order to achieve this stable noble gas electron configuration. The bonding pair electrons are between the element symbols. So they're always shown as dots between the atomic symbols. A line can also represent a bonding pair of electrons. And that's often used on a structural diagram. So if you have H and F, you bring them together, you'll notice that those two are now stable because they are sharing this pair of electrons here. This is called a bonded pair, and these outside are not bonded pairs. This one is called the bonded pair here, being shared between H and F. This is called a single covalent bond, where this bonded pair is located, and can be represented by a line or by 2 dots, but not both. Now, the octet rule to check to see if it works after you draw your Lewis structure. F has 8 around it, 2, 4, 6, 8. Yep. H has how many around it? Only 2, which is what it wants because of the duet rule or modified octet. The Lewis electron dot structures, bonding electron pairs and electron pairs that are involved in bonds. It shows lone electron pairs. These are electron pairs that do not participate in bonding. So these are called the bonding pairs. This is the bonded pair or bonding pairs. These are called the lone pairs. There are 3 lone pairs around HF here. 1 bonded pair, 1 lone pair. So bonding electron pairs are electron pairs that are involved in bonds. Lone electron pairs are electron bonds that do not participate in bonding. The bond order is equal to the number of bonds. So here in water, that's a bonding pair. What about this one up here? What would that be called? Lone pair. What about this one down here? And that one? Lone pair gives you the answer. Perfect. Steps to draw Lewis structures. Draw the Lewis structure of O2. So if we wanted to draw O2, the first thing you can do is you can add up all the valence electrons. So there's 2 oxygens. How many valence electrons on 1 oxygen? 6. What's 2 times 6? 12. So you need 12 dots. This is 1O. 12 electrons. So there are 12 electrons available for the entire molecule. Now, as long as you draw the structure with 12 electrons, you should be good to go. If you add 13, you're wrong. If you add 11, you're wrong. So, the next step, connect the atoms with a single bond. So here's our O, we make a single bond. How many electrons are in a single bond? 2 electrons. So how many do we have left? 12 minus 2 is 10. So sometimes people like to keep track of that. You don't always have to. At the end, just check and make sure you got 12 dots at the end. Then you distribute the remaining electrons to fulfill all atoms until the electron total is reached. So we start drawing. We use 2, we got 12 total. We add more. 6 total, 8 total, 10 total, 12 total. Now we got a little problem. Do they all fulfill the octet rule? No, this one's happy. Yay, I got 8. This one's like, I got gypped. I got 6. All right? So, they're not sharing enough electrons. If you're short on the electrons that are needed, determine how many extra bonds are required. Number of extra bonds equals numbers of electrons needed divided by 2. Oh, that makes it easy. So 2 electrons are needed, divided by 2, that means 1 extra bond is required. So I'm going to use 2 bonds in the middle, and then go again, 6, 8, 10, 12. Oh my goodness. 2, 4, 6, 8. Yep, 2, 4, 6, 8. We're both happy, we're good to go. What's up? So this one here is 2, 4, 6, 8 around it being shared. And then 2, 4, 6, 8 around this O being shared.
Oh, the last time there was only...
There was 6 on one of them. 8 on one and 6 on one, yep. So it's got to fulfill the octet rule for most molecules. So here's another way of visualizing it. Okay, here we got these 2. They come together. Here's the dots. And then you can draw it with the lines. So this electron, okay, you can move the electrons so that they match up better anywhere you need to make it look pretty. Now, here's the next step. Okay, we got that. That works most of the time. If more than 2 atoms, the least electronegative atom is the central atom. All other atoms connect to the center. So, periodic table, real quick flashback. Periodic trend. What is the most electronegative element on the periodic table? Most electronegative. Fluorine, very good. Bullet. The bullet on the periodic table. Now, the least electronegative is francium. So, we're looking for the ones that are closest in this direction here. We write those first. Okay, this is almost always true. Almost always true. The only exception we have to this, sometimes hydrogen is better, but hydrogen is a little bit weird sometimes, but everything else is written in that order. That's why sodium chloride is written NaCl, because Na is here, Cl is here. Carbon dioxide. Carbon is written first, oxygen is written second, because carbon is closer, less electronegative than oxygen. Okay? So that is one general pattern. That's why the left, usually the things that are written first are on the left side of the periodic table in general. So CO2, you got C and 2 O's. So you have to decide which one is going into the middle. It's the least electronegative, which is the C. So you stick the C in the middle. It's got 16 valence electrons. Take your C, move your O's. You do single bonds first. Okay? And you want the outer atoms first. Okay, the most electronegative ones will have, most likely have those electrons closest to it. So satisfy the most electronegative atoms first. So we put 2 there, 2 there, 2 there, 2 there, 2 there, and 2 there. Now, oxygen right now has got the octet rule, but carbon does not. So what do you think needs to happen? Okay, we need to share some.
Doesn't oxygen only have 6? No, because the...
Are all atoms happy?
I know, so that means that makes it 8 valence. That's how much it needs.
So they're not all happy?
No, it has 6, but it wants 8.
So oxygen has 2, 4, 6, 8. Those two, that line represents 2 dots. And there, anything in between is being shared around the oxygen.
There's more than 16 dots around that, right?
Oh, there is?
2, 4, 6. Why is it 16? Oh, it's 16, I can't.
It's okay. I can't either. I probably would miscount.
Yeah.
But I think this one has been vetted for some errors. Medea found the only error I've seen so far. So, So what we got to do is convert lone pairs into bonding pairs so that it satisfies the octet rule. You can use a single bond, a double bond, or a triple bond. Quadruple bonds sound nice, but they don't happen. Sounds like it might happen, but if you had two carbons, you got four electrons, it would seem to make sense. They could just, hook up. But it doesn't work. So, at least as far as we know, it doesn't work. So, triple bonds are possible. So we do the same thing. We've got our, first try a double bond, because it's usually easiest. Take those, turn them into a bond. Now we check really quickly. 2, 4, 6, 8. Yay, that's happy. 2, 4, 6. Is the carbon happy?
No.
Nope. So we still didn't do it. We got to go try another double bond. Okay, now are they all happy? Yep. All happy. Success. We are happy. Yep. You could have a triple on one side and a single on the other. Yep. It's possible. Maybe not in this case, but it's possible. Yep. But most likely, if you had this option here, you would want to balance it out. And there's reasons why it does that. Because both of the O's have the same electronegativity and the C has the same electronegativity. So you'd expect them to share equally or share most equally. Now, if molecule is an ion, for anions, add the extra electrons to the total number available. For cations, subtract the lost electrons from the number available. Don't forget the brackets and the charge. So, carbonate, CO3, 2 minus. If it's got a 2 minus charge, you're going to add electrons or subtract electrons from the total. Add electrons, because electrons are what? Negative charge. So, carbon's got 4, oxygen's got 6, 6, 6. 18 plus 4 is what? 22. Plus 2 is 24. So, we need 24 valence electrons. Yes, sir? Why didn't they? Good question. Yeah. Somebody chose the magnetic fields before electrons. All right. So this is an advertisement for why you should wear your safety goggles. It's over there on the screen now. All right. You don't get it? Yeah, wear your safety goggles. It's actually not even funny, but here's me. Yeah. As a teacher, I want all of you to be able to see when you're done with chemistry. It's my #1 goal. If you see the chemistry, that's cool too. All right. So we got all our C's and O's. Which one should be in the middle? C. So we'll put C in the middle. Put these all around the outside. Now let's start single bonds. Yeah, look at that. That's pretty. All right. Now, what do you have to do next? Are all the atoms happy? No. Oh, it looks pretty, but not all the atoms are happy. So, what do we have to do? Double bond. Where should we put it? Top? Let's see. Where's it go? Let me say side. Left, right? Oh, bottom left winner. No. Doesn't matter. Now, are all atoms happy now? Yes, but, oh no, what? Thought we did it right. What did we forget? Yeah, bracket 2 minus, there you go. Oh, yeah. Now you got success, there you go. Questions, clarifications on that? Yep. Why is there only what? There's only this double bond. We have to satisfy the carbon. So 2 of the electrons come in here. We got 2, 4, 6, 8 around this. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Everybody's happy. But we must have the bracket saying where we got those electrons from. All right, here's the really fun stuff. Here are the exceptions. So, you know the rule, and you have to be aware of the exceptions. There are not a lot of exceptions, but the ones that are exceptions are kind of cool. Sometimes, there is what's called an incomplete octet. This is when it's stable with less than 8 valence electrons. Does not happen very often.
Helium.
Beryllium is one. Okay, beryllium. Stable with only 4 valence electrons. BeH2, for example. Boron is another one. So beryllium and boron, it's stable with 6 valence electrons. BF3 here, boron trifluoride. So beryllium and boron, you'll notice that they're really close to the helium. So they're in the exception area.
Why not lithium?
Lithium, not an exception because lithium tends to lose electrons, not share. So beryllium is really interesting because here it's forming a covalent bond even though beryllium is a metal. Unique of it. This one here, boron, is right on the edge. It's usually referred to as a metalloid. Here it's sharing electrons with fluorine. So that's one of the reasons why they're exceptions, based on their position in the table. N can be stable with 7 valence electrons. Okay, again, nitrogen, unfortunately, it's right after carbon, but nitrogen has some unique properties. The odd electron molecules are called radicals because they are not normal. They're radical. Radicals are very reactive, extremely reactive, because they want to have that stable octet if possible. So that's why they're not stable, but they still can be more stable than they can be found in nature with 7. Nitrogen monoxide is a good example of this. Okay, NO here. The O has 2, 4, 6, 8 around it. The N has 2, 4, 6, 7. It really wants 1 electron. So it's going to try to take electron from anything it can. It wants to be more stable if possible. It's stable, but it's not as stable as it could be. Yes, sir?
So nitrogen has 7 valence or 8 electrons?
It could have 7 or it could have 8, yes. Yeah, nitrogen is one of those exceptions, and it influences a lot of atmospheric chemistry for the Lewis-Dot structure. NO2. Here on NO2, the oxygen is happy, the oxygen is happy. The nitrogen, 2, 4, 6, 7 again. So again, NO, NO2. These are often referred to as NOx's because if you have multiple O's on it, you can have all sorts of different products that are very reactive. Ingredients in smog, for example. So those are the exceptions. Not too many. Beryllium, boron, and nitrogen. Now, expanded octets. Elements that are in period 3 or higher have available d orbitals. So 3 or higher have d orbitals, that's in the d section, that may be used to accept additional electrons if necessary. So this is something where the octet, again, will not apply because it's expanded. If the central atom has available d subshell, it can have more than 8 valence electrons. Ne and argon do not expand their octet. So neon and argon will not expand it. This occurs when the central atom contacts highly electronegative elements, such as fluorine, chlorine, bromine, halogens, and oxygen. This here is a prime example, sulfur with 6 fluorines, SF6. The total valence electrons in SF6 is 48 valence electrons. It's got 48 valence electrons that we would have to put around it. So here's our F, here's our 6 Fs. Move 1 there, 1 there. Those 2 are available. Again, this fulfills the octet, SF2. 2, 4, 6, 8, 2, 4, 6, 8. Everybody's happy, but it still can accept more Fs. Yes?
What were the 2 exceptions to
Expanded octet, yep. expanded octet happens when it has an available D subshell. Neon does not have an available D subshell, so it wouldn't apply. Argon does not, even though it is in the 3p section, it would have a 3b available. So neon, I'm not sure why neon's included as a not expanding their octet, but argon is for sure what I would remember. And it usually happens when they're in contact with fluorine. It's the most electronegative element, although chlorine is fairly electronegative as well. So here, as you can see, we share 2 electrons. 2 electrons, now we have a stable structure. However, more fluorines can react with the expanded octet. The electrons need to be able to be placed into the D subshell for that to happen. So that one gets placed there. That one gets placed there. That one gets placed there. And there's our last one that is expanded octet. Okay, this is how you can have some molecules that don't fulfill the octet rule. So this is SF6. Now, yes? If you just have that you have S and F coming together, you would not know whether it would be expanded or normal. Correct. Usually it would have to do with, it may have to do with the concentration of the F, most likely, the more F's you have. So it would be harder to predict which one if you were trying to predict the reactions per se. But if you were given the formula, then you could go from that. Yeah. All right, for the next one, this is a unique one because in previous chemistry, we've been trying to get all of our atoms like a noble gas. And we've been saying, the noble gases are so happy. But what do you see up here? Xe is a what? It is a noble gas. Noble gases tend to be unreactive. However, they can form compounds like xenon tetrafluoride. So again, this is one of the exceptions to the octet rule. It's also a unique molecule because of xenon bonding with something else. So we add up the total number of electrons, 36.
I didn't get that.
Xenon is here. It has 8 valence electrons because it's in the 8th group. Fluorine has 7, and there's 4 of them. So 7 times 4 is 28, plus 8 is 36. Yes, sir?
Can't you get an aluminum foil boat in this stuff?
Oh, that'd be cool. I haven't done it before, but that would be cool. It's got some really cool properties. Yeah, aluminum foil boat. It's going to be a very heavy gas, for sure. So the next step is to connect the atoms together, right? Electrons remaining, there's 28 electrons left. So where do we put them? All right, just fill them up, 2, 4, 6. Uh-oh. We got 4 electrons remaining.
Double bonds.
So, double bonds, but then fluorine wouldn't be happy with that. Yeah, so it'd be nice if double bonds work, but fluorine wouldn't like it. Xenon, no. So you just stick them in. Step 9. Oh, 9. I didn't know there were 9 steps. It's okay. It's an easy step. You just stick them in around the central atom in their expanded D shell. Apply to the corners is what they call it. And so this here, Yeah, these two here, this is an expanded octet. It's got 6 either bonded or lone pairs around it. 1, 2, 3, 4, 5, 6 around it. Yes, sir.
How come there's not one electron on each of the 4 corners?
The reason there's not one electron on each of the 4 corners, okay? The reason there's not one here is due to the positioning the lone pairs. When you have an expanded octet, the lone pairs, if you had only one electron, it would be reactive and would want to connect to something else. So then you could have XZF8, for example, which might be possible. But these two are more stable together than apart because it's more reactive and it wants to gain that stability. So there's a unique thing that happens here where because of the expanded D octet, these here are represented by 2 dots here in the D shell, so it's not shown as 4 singles because Lewis uses single to mean that they are going to connect to something else.
And also, could the pairs be on a group that is 4 stacked at the corners? Could they be adjacent to each other?
These two? Yeah.
Yeah.
Yep.
That's just random.
Yeah, just chosen doesn't matter. Will not affect any of its other properties. Yeah. Because the fluorine 2, 4, 6, 8 is not an exception to the octet rule. Fluorine does not have more than 8 electrons around it. So if you formed a double bond here, you'd have 2, 4, 6, 8, 10 electrons around fluorine. So fluorine doesn't form an exception. Xenon does, and xenon's exception, as Ryan was saying, I totally agree with you. Why don't you just put them singly? It's based on G.N. Lewis's model and an adaptation of it. His model worked really well for the non-expanded ones. This one starts to get into, well, are they paired up or are they not? You know, what would the orbital? You'd have to go to an orbital diagram to see more clearly where those were located in space. So. But this predicts many of the properties of this molecule, xenon tetrafluoride. So here's the instant replay of what it looks like. Here's your fluorine. Whoa, wait a minute. Yeah, it's just a different way of showing it. Some people see this a little easier because the lone pairs are here in the beginning and they're still there at the end. Now, the next thing in looking at Lewis dot structures is to consider what is called formal charge. Okay, formal charge is something just like bonding and it was completely invented by people trying to explain what's going on. Okay, this is the result of a method of electron bookkeeping that tells whether an atom or in a molecule has gained or lost electron compared to an isolated atom. This is a way of evaluating the validity of Lewis dot structures, like that last one, or the SF one. How do you know it's valid? So to get the formal charge, here's the formula for this. You count up the number of valence electrons in the free atom. Then you minus the number of lone electrons plus half of all the electrons, the number of electrons that are in the bonded pairs. So valence electrons in the free atom well, look at that. Free atoms. All right, so let's look at the formal charge and how it works, what all of these things mean. Okay. The formal formal charge rules. The way it works is the most valid possible Lewis dot structure is the one where the sum of all formal charges equals the ionic charge of the species. So the sum of the formal charge equals the ionic charge of the particular species. The central atom should be as close to zero formal charge as possible. So central atom is close to zero. Any formal charges should be on the most electronegative or outer atoms. So formal charges on outer. So to calculate the formal charge, okay, here we have a carbonate ion that we made before. So the number of valence electrons in the free atom. So in this one here, if we look at oxygen, how many valence electrons does oxygen have on the periodic table? 6. That's the free one. So that's the 6. That's where it comes from. So free means when it's not connected or bonded or ionized or anything else. Just normal electron on the periodic table. Okay. Then we look at this. Number of lone electrons. Okay, how many lone electrons are there? 2, 4, 6. And then how many bonded electrons are there? 2. So half of those, half of 2. So the formal charge for oxygen equals -1. Okay? Individually, yep. So formal charge for the carbon, 4 minus 0 plus half of 8, which equals 0. For this red oxygen, it also equals 0 because 6 minus 4 plus half of 4 equals 0. And the last one is similar to the yellow one on the top. Same exact in terms of its setup. Yellow and blue. Now, if you look at these two have 0 formal charge. Okay, if you add this up, -1 and -1, does that equal -2? Yeah. So the sum of the formal charge equals the ionic charge. The central atom equals 0, check. And the outer ones have the formal charge. This one and this one are on the outside. Now some of you might be going, well, how do you differentiate between the red one and the blue one and the yellow one? You really can't. Just a way of drawing a picture of what's going on. So let's look at formaldehyde. Formaldehyde, which of the 2 possible structures for formaldehyde is valid? So using formal charge rules, which one of these is valid or an actual structure? So we got our carbon, 4 minus 2 plus half of 6 is -1. Oxygen is +1. Hydrogens, each of them, 1 minus 0 plus half of 2 is 0. Then we do the carbon on this side, and the oxygen on this side, and the hydrogens. So which structure is better, the one on the left or the one on the right? Which one's better, left or right? Right, because it's 0, 0, 0. Okay? 0, 0, 0. This is the valid structure of formaldehyde. Okay, the valid structure of formaldehyde. Yes? Correct. However, the reason it is not is because this is a -1, this is a +1. Okay? This difference here, you want each of them to have a formal charge as low as possible for it to be valid. So this here, this structure is valid according to formal charge rules because the 0, 0, 0. And carbon is the central atom here, so it wants to have 0 as well. So oxygen could be iffy, but an oxygen plus likes, on the other one it had -1s every time, so those are the reasons why. So this is how the formal charge rules can help you in looking at a Lewis structure. This here is the structure of formaldehyde, CH2O. So here is another way of doing charged species. This is an alternative to the Lewis structures. So instead of drawing a bracket in charge, you just draw the structure. So this here is the structure with non-zero formal charges near the appropriate atoms. So here, this here is another way of drawing it without the brackets. The O has a negative, the O has a negative. That's the 2 negative. Why is those two? Because remember we checked the formal charges. That had a -1, that had a -1, that had a 0, that had a 0. So if you use formal charges, you can do that instead of the brackets. The bonded ones? Bonded electrons are these here. So for this oxygen here, you're looking at?
I'm just trying to find a formal charge with the top oxygen.
Yeah, so you got 6 free, 6 lone.
Where are you getting 6 low? Oh.
And then plus half of the bonded electrons, so that's half of 1. Sorry, half of 2, pardon me. So it's 6 minus 7. Now, the cool thing is, the cool thing about Lewis dot structures, yeah, Megan? In some Lewis structures, the multiple bonds can be written in several equivalent locations. You can write them in multiple places. All structures have the same energy. So to try to explain this, okay, G. N. Lewis's model, they applied what's called resonance to try to explain that they all have the same energy, and they all can look a little bit different but be the same molecule. So how do you know which one is the correct one? The answer is none alone are correct. The true molecule is a hybrid of the possible structures. The electrons are delocalized, which means they're spread throughout the molecule. They're shared in a more freely fashion when you have resonance structure. Sometimes they even say that there's, instead of 2 bonds, there's 1.5 bonds. Is another way of showing this at times. But let's look at a resonance structure to see how you can apply when, again, you have a place where you can put multiple bonds and they all look the same. So resonance is the use of 2 or more Lewis structures to represent a particular molecule. So here is one molecule called ozone that has resonance structures. You'll notice this one and this one look almost the same. Okay? But here you got a double bond drawn here, here you got a double bond drawn here. Okay? Both of them follow the octet rule, and they do have formal charge of positive in the middle O and negative on an outside O. You use double arrows to indicate it is the average of these 2 structures. So it's an average of the 2. It does not switch between them. So ozone doesn't change. The bond doesn't switch around. It doesn't go flip, flop, flip, flop, flip, flop, flip. It is just one ozone molecule and is the average of the 2 in the way the electrons are located. Yes? What that means is the electrons, instead of there being a double bond here and a single bond here, it's more like all 2, 4, 6, all these electrons can be shared throughout the whole thing. So there's more sharing of the electrons throughout the entire molecule. And it's difficult to determine which ones. We'll try to work on that. Yeah?
So basically, it's the same thing, but there's different ways of being able to write it.
Correct, but you have to show that there are different ways in a resonance structure. Because this isn't the answer. This isn't the answer. It's an average of the two. So that's it's not just you can write it two different ways. It's that it is the average of the two of them, which is the resonance. Now, localized electron model is based on pairs of electrons, and it doesn't deal with odd numbers. So the bond lengths are averaged. So here we've got a double bond is less distance, single bond is more distance, and this here is called a 1.5 bond. It's an average. It's got a single line and it's got a dotted upper line showing it's in between. So its bond distance, the distance of the bond is going to be in between the two. So that's why sometimes it's referred to as a 1.5 bond to represent it. In reality, the distance from here to here is the same as the distance from there to there. So the electrons are shared and the bond lengths are averaged. Here's another resonance structure on the one we just looked at. Remember the carbonate? The double bond could be located at any of those, right? So here's our 3 different resonance structures. You just draw the double arrows and you're set. That's it. That's resonance for carbonate. Okay? So it's just showing it could be at any of those 3 locations. The bottom one shows that they each have a bond of approximately 1 1/3, which you're like, wait a minute. So it's more than a single bond, and it's less than a double bond for all 3 of those. Those are what are called the delocalized electrons. So technically speaking, although it's hard to say, is 2 of the electrons, the way the electrons are shared, they're shared throughout that middle section. Here's a sulfate ion. Sulfate ion looks like this here. The formal charge on the sulfur is +2. The formal charge on each of the oxygens is -1. Here's another way of drawing it. So here's sulfate with all being single bonds. You got +2, -1 on the outside. Here, if you do a double bond, 2 double bonds in the middle, the formal charge around the sulfur is 0.
What was it before?
It was +2. Yeah, when it was all single, it was +2 in the middle, and let me see, -1 on the outside. So if you do double bonds in the middle, this changes the formal charge to 0 for sulfur and -1 for 2 of the oxygens, not all the oxygens. So which structure is better? The one with all singles or the one with some doubles? Doubles. It's a better, according to the formal charge rule, that's what you would expect to see. However, which resonance structure is more likely? The first one obeys the octet rule. The second one is favored by formal charge rules. Elements in the 3rd period and beyond, a resonance structure that obeys the octet rule is more likely. So that means this is the sulfate resonance structure. Because it's in the 3rd row, it has the ability to have the delocalized 3D electrons. So that means the electrons can be delocalized, and this is all the resonance structures of sulfate.
Wait, go back to the other one. You said that obeys the octet rule is more likely. The one on the right doesn't obey.
Right, the sulfur here doesn't obey because it has an expanded D. Sulfur is right here.
Oh, it's one of the
sulfur definitely can have an expanded octet, and it's in the third row. So it's D, the 3D orbitals are all open. So that's why the electrons are able to do this. And formal charge says it would do this. So even though this obeys the octet rule, this is more likely because of the formal charge rule and the expanded octet rule. So obeys the octet rule is kind of a, I don't know if that's a good statement to say that. Obeys the expanded octet rule, which is true. Yeah.
So other third grade and beyond obey the formal charge?
Formal charge is always the better option in general, but especially third period, the third period and beyond, yes, because they have the D orbitals available. So again, there's a lot of different resonance structures, right? Because you've got 4 different O's around it. So you've got lots of different options. You got the 2 O's here, the 2 O's there, the O's there, the O's there, the O's there, the O's there. It's an average of all of those. Okay, so this is the resonance structures for sulfate based on formal charge rules and what we'd expect due to its delocalized D orbital. Now, this here is another one that has a delocalization of electrons. This is a ring structure called a benzene ring. Benzene has carbons that are all the way around 6 carbons in a hexagon. Each carbon only has 1 hydrogen attached. So it currently has only 3 bonds. Carbon usually wants to have 4 to have a total of 8 valence electrons. So what it does is it has a partial bond here and a partial bond here. These electrons are all shared all the way around. And they go around in this ring structure. We don't know how, but they are shared with all of the carbons. This makes an incredibly strong structure called the benzene ring that is in many organic molecules. And this is an application of a delocalized electrons. So, Lewis dot structure practice is on page 405 and 406. Okay, lab 25 you'll want to have with you, of course, and lab quiz number 4 is on 12/2, which is Friday. So you've got 7 minutes to do whatever you would like at this time, except cause havoc. Relax, stretch, whatever you need to do.